We have an exciting presentation ahead of us from Axel Reinsch and Fabian Nowacki from RR Engineers GmbH. And the title of today's lecture is Calcbond, an innovative online platform to perform adhesive joint design and calculations. Ladies and gentlemen, enjoy.
Thank you, Bastian, for your introducing words, and welcome from our side as well to our presentation of Calcbond, our web tool for adhesive joint calculations. I'll just briefly introduce myself and Fabian himself, and then we go into the presentation. Yeah, as I said, I'm Axel Reinsch. I'm boat builder and aeronautical engineer. All through my life, I was working with composites, and especially after my university time, I started doing lots of projects with simulations, and this is what we do here at Airbus at AR Engineers as well. So, Fabian, you want to?
Yes, good morning from me also. Fabian Nowacki is my name. I am also an aeronautical engineer, and my work here at AR Engineers includes industrial projects with lightweight engineering, especially with numerical simulation and composite materials. I also engage in R&D projects together with our associated research partners. And finally, I'm responsible for the technical development of our new software tool, Calcbond, which we'll present today.
Thank you, Fabian. So I will now briefly introduce you to AR Engineers and what we're working on here every day. And then Fabian will give you a technical background for Calcbond, and then give you a live app tour. So we switch to our to the internet, and Fabian will give you a tour through the Calcbond app, and then finally I will show you our current developments, what we're working on, and what we see will be online within the next half year. AR Engineer has been founded by me in 2010, and the focus of the company is basically my focus. I've been done all my life through, and that is definitely composites. 99% of the material we work on here is the composite material, because we work in the lightweight industry. The FEA area is the FEA method is what we use here every day as well. So these two fields are the main, the core fields we are working in. As we are an engineering company, the production is, we don't produce by ourselves, but we work a lot with our clients in their production. We help them to do the technical, the technical part of it, so drawings and mold design and so forth, and production supervision as well. So we look after the production is working in the way we were planning it beforehand. We have research and development projects ongoing, especially in the field of material science. Structural health monitoring is a point for us that we're working on a lot. And of course, the area of adhesives, especially the fatigue behavior of adhesive, is one of our research projects we are having. And this leads me to the software field. For us, the engineering has changed a lot, especially in the last years. As simulation engineers, we have always been pushed to do our own programming inside our commercial tools in the FEA field. But especially in the last years, this has changed a lot, because we were forced to do a lot of programming to customize programs for our clients, and that brought the point of software up for us. And with that field of adhesives, we got to the point that we want to provide this back to our clients. So this is definitely part of our doings today. And this is as well our mission. We want to do innovative engineering and bring this back to our clients, so to be more tangible, efficient, and faster as well. Everything has to be faster and efficient today. That's definitely a big point for us. And when I look back now on the last 10 years, the tasks we're doing today have to be done in half of the time, and we have to do double the works, put it in these words. And this is only possible if you rethink what you're doing every day, and programming and software is a big point for us. So and this brings us to Calcbond basically. The fields we're working on is the lightweight industry, because this covers actually all different fields of of industry we're working in. But the ship industry is definitely a big part for us. This is what we do here now in Germany. But offshore wind energy is definitely two big parts we're working on as well. And automotive and rail came up in the last 2 years, where we do a lot of lightweight design and engineering. A few years ago, we had a huge project, probably one of the biggest projects we had so far, was in the field of amusement rides. We were asked to do some design work for composite parts in a roller coaster. And these parts had to be bonded to the steel structure of the train. And we were doing our normal way of engineering, means we had to model the entire train in the FEA environment, and then do the adhesive stress engineering as well. And it was a big challenge for us. We made it, but then we thought that this is definitely worthwhile to look at, because there was no tool for us, especially in the early stage of this project, to do some pre-design for the adhesives to be sure we are on the right way. We did that all with our big FEA model. So this was the point when we started to research and move on with adhesive stress engineering. And and this leads us to Calcbond definitely. And I'll move over to Fabian.
Yes, thank you very much. So why did we decide to start developing the Calcbond software tool? Well, as lightweight engineers and experts in the field of structural engineering and adhesive technology also, we are very convinced of the high potential adhesive bonding has in lightweight design. And if done properly, it can help you save a lot of time, money, and in the end, structural weight of your components, if you can use proper techniques to design and verify your bonded structures. But, and the big but is, the behavior of bonded joints is very complex, and the theory behind it is quite complicated, with lots of variables affecting the mechanical performance of your adhesive joint. And this is often very difficult to put into practice, as our own experience has shown in the past, but also the experience of our clients and other partners of the industry. Just to give you a brief overview of what goes into the equation when dealing with adhesive joint design, you should always answer at least these key questions when you're starting your design. Of course, you have to assess your global structure and identify where your global structural joints are located and how you want to distribute these loads through the connections. So which areas in your structure are the most critical loaded areas, and how do you want to transfer loads within these component and transitions? And then, of course, you have to ask yourself, is adhesive bonding even a suitable, let alone the optimum solution for your job? Maybe you have some manufacturing constraints, which also give you the idea of maybe using another method like bolting or riveting or something, or welding. But if everything is suitable and you're sure that you can apply adhesive bonding in your structure, you can then move over to the next question, which should always be, are there any technical guidelines or rules that apply specifically to my task? So are there technical standards that apply not only to your structure in general because of industry standards, but also to the adhesive bonding process in particular? And additionally, also your company internal regulations may address the adhesive bonding process and the design of structural connections, which always also has to be taken into consideration. And finally, of course, you need to consider which type of adhesive is even suitable, let alone certified for your job. Because of the different industry-specific rules, there could be a limited pool of certified adhesive materials that you can use for your job, despite the mechanical properties. And then finally, of course, you have to check if you have all the necessary data, material data, to perform sound joint design. So when you're starting with your preliminary structural design for your adhesive joint, first, as mentioned before, of course, you'll need to identify the overall structural loading situation. You can do this by conducting global finite element analysis, for example, or basic hand calculations even, or also testing, or a combination of these three methods to define the most critical structural loads. Also, you of course have to define your joint geometry. So which type of joint geometry can you or do you even need to apply? Maybe also dependent on some manufacturing constraints which allow for maybe symmetrical double lap joints instead of asymmetrical single lap joints, or even more complex joint geometries. And this is important because these aspects have a high impact on the critical local joint loads. So depending on your joint geometry, you have different types of loading situations within your joint. For example, like an asymmetrical lap shear loading or bending loads or torsional loads, or also a combination of these different loading types for multi-axial loading scenarios, which mostly occur in reality when you assess your structure overall. Then also a very important aspect is the adhesive material type, because different adhesive types exhibit highly different elasticity behavior, like the stress strain behavior, which also strongly affects the way your adhesive joint performs, and your adhesive joint may fail if failure is something to be taken into account. And once you have looked upon all of these topics, you can then start performing your preliminary design. For example, based on best practice methods. Here in Germany, we have the VDI 2014, for example, which addresses composite structural design. Also, you have the DIN 6701, which is a very good standard for designing structural components with adhesive bonding in the railway industry. And these standards, and also other standards in the German industry, specifically address the adhesive bonding process, and in particular the design by calculation for adhesive joints also. And with these tools, you can then check if you have considered all the best practice design rules there are to be considered when designing your bonded joint. So from the mechanical point of view, let me give you an overview of important influences on your joint performance. Of course, there are environmental conditions that are needed to be taken into account, because industrial adhesives are always based on polymeric materials. So they're highly dependent on the influence of time, the influence of temperature and moisture, which greatly affect the stress strain behavior, as well as the strength and the failure behavior of your adhesive layer in the end. Then you need to consider the highly nonlinear behavior of ductile or elastomeric adhesives, which complicate the calculation process even further, but need to be taken into account when defining material laws. And then also, because or dependent on the geometric configuration of your joint, you tend to have highly non-uniform distribution of loads within the adhesive layer. So the stress distribution, for example, in the adhesive layer is very non-homogeneous. So you tend to get stress peaks at the overlap edges in the transition zone between the adhesive layer and the adherents, which are most likely the first points of failure in the bonded structure. And then, especially when working with composite materials in the adherents, you also have to closely look at the transverse stresses, for example, that are being transferred in the adhesive layer, because these can induce premature failure in your laminate, for example, delamination, because composite materials tend to have a very low transverse strength compared to other isotropic materials, such as metals, for example. And last but not least, with ductile materials in the adhesive layer, you also need to take into account stress reduction effects due to plasticity of your adhesive when reaching the yield strength, for example. So this can actually be very beneficial to your design, as you can actively reduce stress peaks at the adhesive layer edges by considering the plastic deformation of your adhesive layer, if that is something you can allow in your design philosophy. Yeah, and just some of the primary influence factors when designing adhesive bonds are, of course, the adherent and adhesive stiffness, so material values such as the Young's modulus and the Poisson ratio, but also the thickness of these components, because they are the most critical driving factors for the overall joint stiffness and thus the load transfer weighting between the different components. So which methods can you actually use to calculate your bonded joints? First of all, there's always the possibility of basic hand calculations. For example, calculating the average lap shear stress in a single lap joint. However, this, of course, this is really simple, but however, this doesn't give you proper insight into the actual behavior of your joint, because you're only calculating one value, which uses a reference from a standard test, but it doesn't give you any info about different loading scenarios and how your joint would behave under different loading combinations. A better way would be to perform stress analysis with closed form analytical solutions. There you can calculate one-dimensional or sometimes two-dimensional adhesive and adherent stresses and their distribution along the bond surface. But this is often quite complicated because the theory behind it is complicated, as I said before, and it needs some experience in structural mechanics, so to speak, to properly employ these formulas. And the third way, and definitely the most precise way in theory, would be the finite element analysis, of course. So you could use a commercial FEA tool to model your adhesive joint, your adherence, your layers, and perform 1D, 2D, or 3D stress analysis of your adhesive material and the adherence. You can do linear static analysis or non-linear static analysis for large deformations or for plasticity, and get a very precise insight into the overall structural performance for nearly arbitrary loading conditions and also influences such as time and temperature, for example. So once you've chosen which method you want to use, or if you want to combine these methods, of course, you have to define how you want to assess the adhesive safety or adhesive joint safety. And therefore, you have to consider the three different types of failure mechanisms that can occur in your bonded joint. The first would be the cohesion failure, so the rupture of the adhesive layer itself due to overloading or exceeding the, for example, tensile strength of your adhesive material. The second would be adhesion failure, so debonding of the interface between the adhesive layer and the adherent layer. And the third failure mode would be the adherent failure, so the adherents themselves could also fail due to maybe plastic deformation in metallic adherence, or due to, for example, transverse rupture of the adherence, for example, in composite laminates. And finally, of course, you need to verify your calculations, and this can be done on different levels. The first level would always be verification of the adhesive itself. So you could perform bulk adhesive testing, complying with different industry standards and measure values such as the Young's modulus, tensile strength, and so on. You can also perform coupon testing, so you could manufacture bonded joints and perform standard loading on these to assess the overall bonding strength of the joint. And of course, also you have the component level where you would manufacture the small structural assembly of your system, including some of the adhesive joints, and put a more realistic multi-axial load upon the component, so to speak. And the highest level, of course, would always be the entire system test. So if you have a large structure with lots of different connections and a very complicated loading situation, you could also choose to build up the entire assembly with all of the bonded joints and other connections included, and then perform real operating conditions and real loadings if you have the time and capacity and money, of course, for this. All right, and well, how does Calcbond fit into the bigger picture of this adhesive joint design process? Calcbond is a software tool which will help you in your design phase and also in the verification that you have properly designed the joint based on sound structural mechanical methods and mathematical methods. It provides, right now in the beta version, fast and easy to understand analytical lap joint calculations to calculate your stress distribution in the adhesive layer. You will gain access to an extensive engineering database of adherent materials and adhesive materials also. And this results then in a clear display of the different stress distributions and strength results, and you will have a good overview of the most important results and values within the web tool. And finally, this will also be included in an automatically generated PDF report that is being generated once you have done your calculations and you want to work with these results in a very well-structured and just nice to the eye format in a PDF report, which you can save offline and share with coworkers also. Okay, then I would just switch quickly into the live app. So here we are in the browser, in the web browser, at the landing page of our Calcbond tool. And right now you can gain free access in the beta phase. And you can either register via mail or via Google account or via LinkedIn account, for example. So right now I have logged in via my Google account here. And on the left, you can navigate to the Adhesive Joint app, which I'll be demonstrating in a minute. And also you have a calculation history where you can save and reload older projects. We have a frequently asked questions area. We have a wiki with information about adhesive bonding technology in general. And we also have a feedback area where you have the opportunity to give specific feedback if you like. All right, so now to demonstrate the toolbox. First of all, let me show you our material overview. So as I have mentioned before, you will get access to engineering data of different adhesive materials. So this is an exemplary pool of our internal adhesive material database, where you can check on engineering values, also for isotropic adherent materials, and also for composite adherent materials, which can be used to build up laminates for the adherence. And here you can see 3 different types of typical load cases, which can be calculated within our toolbox. So here on the left, you have the most general single lap joint, which can undergo arbitrary loading at all 4 overlap edges. In the middle, you have the standard lap shear joint, which can undergo edge loading, not only tensor loading, but also bending moments and shear forces. And on the on the right side here, sorry, you will have a double L joint connection, which can also undergo bending loads and shear force loads and tensor loads, and also a combination, of course. So let me use the middle load case here. So here we would now be able to define the geometric parameters of our joint. So the joint width, the overlap length, and I'm not going to change the other values, but of course the adhesive layer thickness and also the free length of the adherents 1 and 2. And then you can choose from the pool of adhesive materials, and you can always have a quick look into the most important engineering data here, but also you would be always able to define your own values if you have internally tested data, for example. But for this example, let me just stick with a moderately high modulus adhesive, structural adhesive. And in the next step, we would be defining our adherent materials. So the thickness of the adherence is always an important factor, and also the engineering material itself. So you could choose from typical engineering metallic alloys, but also engineering plastics if you like. Or you could even design a composite layer with a generically generated composite laminate based on different unidirectional GRP or CFRP plies. And then you would quickly get your most important engineering values based on laminate theory, which are directly sent to the adhesive stress analysis tool. And here for the adherent number 2, I would just leave it at steel. And yeah, then you could also already start the analysis by clicking on this button here. Or if you want to go further into the details because you're familiar with some solution methods, maybe you could choose by hand which solution method you would like to be work with. But in this case, I would just leave it at program controlled. And then, oh, I forgot something actually, of course, you have to define the loads. Yes, sorry. So here in the last step, you would see the loading scenario for your lap joint. Here at the left side, we have a fixed support of the first adherent, and here on the right side, we would have separate or a combination of tensile loads, shear forces, and also bending moments. And you can define these separately or in combination. And then you press on the button and the calculation is done. So now you have an overview of your input data, all the forces that are being calculated in the overlap sections. And here you have an overview of your input data for the adherence, for the adhesive, material data, but also the geometric parameters. And finally, you will get your stress analysis results. So you have the stress distribution along the bond length in the adhesive layer. Here we have the peel stresses and the transverse shear stresses of the adhesive layer. And these are also directly being transformed into inverse reserve factors, which are based on suitable failure criteria for polymeric materials. And here you can see if the inverse reserve exceeds a value of 1, here, for example, would be, you would have the information that here, this area near the edges is exceeding the adhesive tensile strength. And this gives you a nearly instant feedback for how your joint performs and how much of either reserve in the safety of the adhesive material or in exceeding of the safety you have here. And finally, if you want, you can save this project. You can give it a distinct name and save the calculation, which can then be accessed in your calculation history. As you can see here at the bottom, the very last row is the project from today, so October 20th. And you can click on the link and get back to the exact same page with all the specific data. And finally, you have your PDF report, which is generated from our server in the back. And now the connection is a little bit slow. Here we have it. And here you can see the document with the most important information at the bottom, with the name of the person that generated the report, with the date, and an overview of the most important chapters. Here you can see the input data of your joint geometry, your loading scenario, your adhesive material data, and of course, a graphical and also tabular overview of the results, also with text passages to help you properly understand all those numbers and how to interpret them to evaluate your adhesive safety or the failure. And finally, you will have a last page with an overview in the most important information about the toolbox and our company, of course, and also with a direct link to your calculation. So if you share this PDF digitally with friends or colleagues, they can click on the link, and if they're registered, they can access this specific project instantly. Okay, so that's all for the live demonstration for now. And now I would give back to Axel to tell you about the current developments.
Thank you, Fabian. I think that was a really great tool, and it has shown that Calcbond is on a really great stage. We're still in a beta phase, as Fabian said. So we're not spreading the link so far at the moment, but if you're interested in using it as a beta user, you can definitely drop us a line, send us an email, or give us a call, and we have a chat about install you as a beta user in return to get feedback from you. So that's definitely what we're going to do, what we would do if you're interested in that. We're still in the beta phase because we're still in development of a few big or a few really interesting big tasks that I want to present to you now. The first one from the left, load case conversion tool, is what you have seen already online with the single lap joint. You are able to enter external loads instead of section loads. That's very much easier than recalculating your own section loads, because this way it's less vulnerable, and very often as an engineer you come with external loads into the game, so it's it's just more straightforward. The automated finite element analysis tool is something I will present on the next page, but of course at the moment we do analytical calculations, and what we want to do is we want to go further forward and be able to calculate fasteners or joints that aren't possible to calculate with an analytical approach. So we need FEA for that, and we are about to we are developing a tool that's where the FEA code is embedded in our system. The composite calculation is for us very important because we are an engineering company doing composites every day, and of course we would love to have this on our platform as well, and we're working on that in the same way. And as well, we want to be able, as Fabian presented already, we want to extend the composite design tool for the adherence on the other hand as well anyway. So that's on our list, definitely. The bottom-up approach on the very right is probably the most challenging and the less tangible process, but I will go in detail with that on another slide as well. So I'm looking to the automated FEA routine. For those who know what FEA is, it's a system where we can do numerical simulations with complex structures. The way it works is that you have material numbers, you have the geometry, you have loads, and you put it all into one system on your commercial tool. You run the solver and post-process the results, and this process we've embedded in our system, or we want to embed it in our system in a very good way. And we do it in the way that you online go on our platform and you pick the system you want, the fastener or your joint system you want. You have to decide for the material of the fastener or the adherence. You have to put in all the numbers that are important for your structure. You enter the loads and then you run the solver. You request the FEA, it's sent to the web server, and from the web server to our local server here in Hamburg. And our routines will put the FEA model together to a 3D model and solves it and does the post-processing, and then results will be streamed up to our web platform again. And you can review, after a few minutes, you can review your results on your account. This will be done either through tables, so you can just review the numbers in the way that Fabian has presented the Calcbond results at the moment. And but as well, and this is the big advantage for FEA, you will as well get 3D plots. And these 3D plots are not only with the adhesive results, but as well with the fastener stresses, the substrate stresses, or the deformation of the entire system, and that's a really big advantage. And as well, we can run structures or joints that are more complex than just a single lap joint. For the joint optimization, which is the bottom-up approach, for us, it's very, very, very interesting and very important for us to bring that to our users, because the way it works before and the way I presented now, the FEA, the automated FEA process, is that you have all these numbers ready. You have to choose your design before. You have to choose your constraints before. You have to choose your material before, and then you run it and you get one result. And this result may be the result you want to see. Very often in the beginning of the process, it's result you don't want to see. The reserve factor is too small. The joint isn't the right one. It's just not there where you wanted to have it, and you have to rerun it. And to be able to rerun, you have to take the decision, what do you want to change? And then you run it again, and you might find out it's still not where you want to have it. And you have to do it again and over again. It takes time. And as well, you are committed to do the right decisions, and then you end up at one spot where you're happy. And most of the time, it's somewhere in your system where you want to be, but it's not necessarily the ideal solution. So with this bottom-up approach, we flip the process. you just define the goals you have in your joint. So that could be that the reserve factor is larger than 2, or some other constraints like the type of material also, and so forth. And then you need, of course, some loads, and then you run the system, and the system will give you back a variety of results from where you can pick your system. So in this way, you can then choose, okay, I will go this way, I will go that way, because the system will figure out, okay, you've got a range of results that are around the reserve factor of 2. Some will be a little bit below, some a little bit above. The material range will be and will be in the stiffness range or in the strength range. And then you can choose, okay, I want to go this way or I want to go that way. And you do that just within minutes. And the big advantage here is that you can do all this without pre-decide for some points that for some values or some factors that are necessary to run the model. The system will do that. And the second big advantage is that you don't need much experience about optimization or about FEA code. You can just do that by clicking through the system. Composite calculation, as I said, is very important for us because we are living composites here every day, and we would provide this functionality in the same way that we provide the Calcbond functionalities at the moment in combination with the automated FEA. So you can click through a variety of standardized composite components. You have your loads ready. You have an idea of your laminate. You enter the laminate, you run it, and you get your results just within minutes. You can decide whether the beam or the tube or the plate or the panel is strong enough or needs to be reinforced as well. And that's, of course, not necessary to say to combine this composite calculation functionalities with the optimization functionalities is something that we see for next year as well. So you would combine optimization algorithm with the composite calculation and get a very, very ideal situation for your standardized composite components. Yeah, and this is basically what we're working on today. And as you could see that for us, it's very important to provide web-based, high-quality automated engineering as a service for the lightweight industry, because we think that's the way it's going to go anyway. And we have to be faster with our decisions. We have to be early in the process of the projects to take the right decisions. And to do that, we need to be as fast as possible. And those tools, like our Calcbond tool, is one very necessary step to be able to do that and to be ready for the future. For our Calcbond tool, the vision is, and that's very obvious, I think, as well, to provide the first online adhesive joint toolbox to run sophisticated design and analysis with access to extensive engineering data, as you have seen, and to provide fast, reliable, and transparent results. And I hope we could show that in the last half an hour with our Calcbond tool and our online demonstration of everything, and with the outlook as well, what's going on in the next 6 or 12 months. And we hope that has shown everything what we're doing here, and that's a great thing to do. So thank you for your attention, and if you've got questions, just feel free to ask. Thank you.
Yeah. Thanks very much.
Thank you very much, Mr. Reinsch and Mr. Nowacki, for this, I think, very interesting and impressive presentation.